In this video, I'm going to give you some information about um, linear vector fields in the plane in the case of complex eigenvectors and complex eigenvalues. So just to refresh your memory, you can sometimes have complex numbers lambda that satisfy an equation like this, even when A has only real entries. I'll say more about that in another video. But it means that there are some things that you have to kind of be aware of when solving differential equations. Here's the problem. Okay, so let's suppose that lambda is equal to alpha plus I times beta, and alpha and beta are real and I is the complex unit. Well, a couple of things to note. We can also break up V into U plus IW, so U and W are real valued vectors. Then it turns out that the conjugate of lambda, alpha minus I beta, and the conjugate of V, so U minus IW, are also an eigenvalue and eigenvector pair. And just so that it's clear, I'm assuming that A is a real matrix. This is not necessarily going to work if A is a complex matrix. But if A is a real matrix, then what happens is you can start with this equation, AV equals lambda V, and take the conjugate of both sides, and you'll get this result. But since A is a real matrix, it is equal to its own conjugate, and that takes us to this equation. But now what are we going to do about the fact that we're supposed to be able to get real solutions to x dot equals ax? You can prove that there are always real solutions to this equation, even when the eigenvalues are complex. Well, the solution to this is that you start with complex solutions, and you can construct these a couple of different ways. So let me do here e to the lambda t, lambda 1t times v1. But then if I take the conjugate of both sides, yeah, let me leave the v's out of this. Sorry, the subscripts out of this because we don't need them. The solutions will come in complex conjugate pairs. Again, assuming A is real. And the reason for this is nope, I need to put a bar right there. That was a mistake, sorry. Okay, so the solutions come in complex conjugate pairs. And again, you can simply take the derivatives with respect to t of both sides, and you'll be able to make that work. Well, the space of solutions is a vector space. So I can take linear combinations of vectors, of solutions, and get more solutions that way. Well, so if I take z and break it up into a real part plus I times an imaginary part, just like any complex number and its conjugate, if you add z to z bar, the imaginary parts will cancel out. So if I take z plus z bar, I end up with e to the lambda t v plus e to the lambda bar t v bar. And if I put 1/2 in front of all of this, I will end up with just the real part of z. And since this is a linear combination of solutions, this is also a solution to x dot equals ax. And so I'm going to call this x1. Likewise, if I take z minus z bar, that'll give me e to the lambda t v minus e to the lambda bar t v bar. And if I put a factor of 1/2, you'll see that what happens is that the real parts cancel out, and I'll be left with twice the imaginary parts. And actually, to make it real, I need to divide by 2i. Sorry about that. Let me make it 1 over 2i. So this is also a solution to x dot equals ax. This is the imaginary part of that complex solution z, and I'm going to call that x2. Okay, so at least in theory, we're good. But what do these solutions look like? Well, here's where we need to do a little bit more with complex numbers. I'm going to return to z equals e to the lambda t times v and fill in the real components. So e to the alpha plus I beta times t, and then u plus I w for v. And actually, let me leave it like this for now. So then, when I expand all of this, first thing that I can do is bring e to the alpha t out front. That's just a real factor that comes out in front of everything. So that leaves us now with e to the ib t times u plus I w. But now there's an important thing to know, which is the connection between e to the I theta and the trig functions. E to the I theta can be written in polar form, is written in polar form, but it can be written in rectangular form as cosine theta plus I sine theta. And that's sometimes called Eulers' formula, and it comes from the power series for the exponential function and the sine and cosine functions. I'll talk about that later if you like. E to the alpha t now can be written as cosine beta t plus I sine beta t times u plus IW. Now I'm going to expand all of that stuff and collect the real and imaginary parts separately. So for the real part, I'm going to get cosine beta t times u minus sine beta t times w. Then for the complex part, I'm going to get sine beta t times u plus cosine beta t times w. Remember that what we did up here was to show that the real part of z and the imaginary part of z are both linear combinations of z and z bar, both of which solve the differential equation, which means that the real and imaginary parts here are the two solutions in real form. So yeah, are two real solutions. So let me write this: e to the alpha t times cosine beta t u minus sine beta t w, and the imaginary part is e to the at sine beta t u plus cosine beta t w. So that gives us entirely real formulas for two independent solutions to the differential equation x dot equals ax. Right, so we're still working with a real matrix A. We've got this. We were able to use eigenvalues and eigenvectors to find two solutions using complex numbers, and then we took linear combinations of those two solutions, which happen to be complex conjugates. That gave us the real part and the imaginary part. Both of those are solutions, and it turns out that they are linearly independent, which means that every solution in entirely real functions is some linear combination of x1 and x2. Now, what do these look like? Yeah, what do these look like? So here's part of so here's how to make this work. So let's just first focus on this one. Okay. So u and w are vectors. The cosine part and the sine part are going to oscillate. The e to the at part will either grow or decay depending on whether a is positive or negative. So the two parts to this, so let's suppose, for example, if a is less than 0, then the x1 is going to have two components, one of which, both of which are going to look something like this. They're going to be offset by a phase difference, and the scaling may get a little bit complicated, but roughly speaking, they're going to be oscillating and decaying as time advances. On the other hand, if alpha is greater than 0, the e to the alpha part will grow, and the cosine and sine parts will oscillate, and that'll give solutions whose components look like this. When you put all of this together, so this is, sorry, let me make this t, and then this is x1, 1, and then x1, 1, let's say. If you now draw this in a phase plane, you're going to see solutions that spiral inward for a less than 0, and for solutions where, for differential equations where alpha happens to be greater than 0, you'll see solutions spiral outward. Let me show you some pictures. Okay. Now I've set this up just a little bit differently from how I did it in the notes up there. This is actually minus W, and the reason for that is that it just makes it a little bit easier to see what's going on. So there's u and there's minus w. You can see that what the eigenvectors control is how oblong the spiral is. So if they're almost the same, you get a very even circular spiral. Well, I say circular, but in the sense that it's got a high degree of rotational symmetry. Whereas if one is much greater than the other, you'll get this very oblong spiral where it overshoots in one direction and comes back. I'm using alpha less than 1. If I increase this to where alpha is now positive, the difference is that the solutions are spiraling outward, whereas with alpha negative they were spiraling inward. For beta, changing beta around basically changes the direction of the spiral. So when beta is negative, you can see spiraling happens in this clockwise direction. And when beta is positive, they go in the spiraling goes in the counterclockwise direction. And again, just to make this picture a little bit neater, this purple arrow is u, and this green arrow is minus w. So that's a quick introduction to what these what solutions look like in the case of complex eigenvalues and eigenvectors. I can give you some names. So these are now called a stable spiral and an unstable spiral. If it happens that alpha is equal to 0, well, then the solutions are simply cosine beta t times u minus, I believe I'm getting this right, minus sine beta t times w. And in this case, there's no growth or decay. The solutions simply trace out ellipses. And if I go to my numerics here and just make alpha exactly equal to 0, you can see that the solutions actually trace out perfect ellipses. The eigenvectors control how eccentric the ellipse is. So if they're almost, or sorry, I should say the real and imaginary components of the eigenvectors control how eccentric the ellipses are. So here they're almost the same magnitude, and here one of them is very long and the other is very short, and you can see that that controls the eccentricity of the ellipses. Something like this is called a center. And for reasons related to conservation laws, centers show up a lot when you're dealing with Hamiltonian mechanics. But since it requires a very specific condition that alpha has to be exactly 0 with no wiggle room one way or the other, for most dynamical systems, you're not going to see a perfect center. If you do, it probably indicates a bifurcation is happening. So that will be the topic of another video.